Okay, okay, thank you for the very great introduction. So my name is Jungdam from Meta AI. So today I'm gonna talk about the motion and behavior generation for virtual agent in Metaverse. So it's about some applications for AI, but also I'm talking about somehow the connection between the AI and the graphics and some of the visions as well. So yeah, good. Recently, I guess you maybe hear the word metaverse many times from here and there. So let me start with briefly explaining what metaverse refers to for those of you who are not familiar with this concept. This terminology was first introduced in the science fiction novel Snow Crash, which was in 1992. In the also telling metaverse was a shared virtual universe that many users are connected simultaneously. So that universe resembles to the real world, where there exists tangible objects like road and buildings, and there are also intangible concepts like economy or culture and so on. So after then, Ernest Cline also used the similar ideas in his science fiction novel, Ready Player One. And one of the most famous film directors, Steven Spielberg, made a movie based on the novel in 2018, which was shown on the right. So the video on the right is actually the trailer of the movie. So where the main character wears a VR headset and some special clothes, and which enables the character to interact with the other people in the virtual world. In summary, the terminology originally only refers to a virtual world that is so similar but independent to the real world. However, nowadays, metaverse does not only refers to virtual world only, rather it refers to the entire spectrum of augmented reality. Here we have some popular applications that are currently have considered as metaverse nowadays. The first one is examples. The first one is a Google Map and 3D Map. They are also considered as metaverse nowadays because it allows users to look around some distant places without physically being there. In the second, we have some augmented reality applications, for example, arranging furnitures virtually to see if they look great on your in your living room or in your house, which is also considered as a metaverse nowadays. In the middle, by using special VR and AR devices, we can use virtual monitors and keyboard while you are working at your desk. And next, you can also chat and work with your friends in a 3D virtual space. And finally, in the extreme case, you may not notice the difference between the real users and their virtual avatars when using it. So we have a really large spectrum of metaverse nowadays. But in this spectrum, although they all have great potentials and they have many interesting topics to discuss, I'm especially interested in these three applications which can provide immersive experience to users. Okay, let me show one concrete example that falls under this area that I mentioned before. This is a Metaverse application called Horizon Workroom. In the current 2D video chat like Zoom, what are the missing items that prevent effective communication for us? I think I would say the three reasons, which is the first one might be the users cannot look at each other's eyes due to the mismatch between the camera and the screen. The second one might be the use of gestures are quite limited, unlike real in-person discussion. Finally, the way of using extra tools that require physical interaction, such as writing something on a blackboard, is different from what we have been used so far in real life. So it takes quite a time to learn those tools in the 2D video chat. But many metaverse applications for video meeting, including Horizon Workroom, as shown here, are designed for resolving such issues. just one requirement is that users need to wear a VR device, such as Oculus Quest to, sorry. One thing that I want to emphasize in this talk is that human motions are quite fundamental means of communication in Metaverse applications, and those motions are delivered each other through 3D virtual avatars representing users or other entities. So the system should have technical components that can efficiently understand and process human motions while reproducing plausible motions for 3D virtual avatars. So after I joined the company, I have been studying for the method to create natural and plausible motions for 3D virtual avatars. From my perspective, I think that virtual avatars can typically be classified into two different types. One is a user-driven avatar, and the other is an autonomous avatar. During the remaining time, I will cover recent research progress for each cases and explain some technical details if the time is allowed. Let's have a look at user-driven avatars first. So user-driven avatars literally means avatars whose motions and behaviors are directed by users. So the goal is basically to copy users' motions as close as possible to their avatars as shown in the left figure. Practically, users will be equipped with some hardware sensors, and we want our algorithm to reproduce users' full body motions based on those sensor input signals. If you look at the input and the output of the model, that what we really want to do is building a real-time motion capture system. So the most popular commercial solutions for that are marker-based optical systems, as shown in the screen. So in those systems, to capture your body motions, you need to we need a large space enough to install multiple cameras. Most manufacturers usually require a minimum of 4 cameras to be installed, but in practice, we can install more than 8 cameras so that it can cover the entire capture region. Then actors need to wear specially designed suit and then put many markers precisely on the designated body parts. As shown here, you need to put a lot of markers on your bodies. Then finally, we also need the calibration process that typically takes several minutes. But due to the high precision, actually this kind of system have been widely used in many serious applications such as filmmaking or medical industries. However, we know that these are not practical and ideal solutions for novice Metaverse users when considering that the system setup and the actual cost to buy a system. Actually, these kind of systems are quite expensive. For example, the minimum price would be a few $1,000s, and the price sometimes can go up to $100,000 depending on the accuracy. Among many possible options, so definitely because we don't want our users to buy such an expensive system or wear some kind of special suit, which might be burdensome. So we want our users to use a very lightweight motion capture system, and then we hope that the motion capture system is potentially very cost-effective and very easy to use. So among many possible options for that, so currently the inertial measurement unit has been thought as one of the optimal sensors for VR and AR applications to capture users' motion. So IMU is a device that includes gyroscope and accelerometers and sometimes magnetometers. So it basically measures linear acceleration and angular velocity of an object to which it is attached. IMUs are actually popular these days. For example, the cell phones, smartwatches, and gaming joystick and VR controllers are already equipped with some IMUs in it. For example, when changing the orientation of iPhones, you may know that the screens automatically rotate. I think that is where IMU sensor inputs are used. Okay, the IMU have unique benefits over the other sensors, such as vision-based sensors. So first, it can be made very small and cheap, which is ideal property as a wearable sensor. Using many sensors does not cost that much, you know. So, and the waterproof option is also available nowadays. Second, IMU sensor signals are insensitive to external conditions such as occlusions or light. So it can be used from almost everywhere, regardless of it is indoor, outdoor, or day or night, whatever. Finally, it has much less privacy issues when compared to the vision-based sensors. So when using the IMU sensors, we don't have to worry about our face being captured when using the system, actually. Okay, then let's be more specific about the problem that we want to solve right now. The input will be a sequence of IMU sensor inputs attached to user's body, and the output will be a user's full body motions, which is a sequence of joint angles, where we assume that we already have a user skeletal model. In theory, in theory, we can track a single 3D positions and orientation from a single IMU sensors. So a full body motions can directly be reconstructed if we attach IMU sensors on every joint and every body on our every bodies and every joint. But practically, people are more interested in using smaller number of sensors. For example, we could use 6 sensors, where one sensor on the head and one sensor on the waist, and 2 sensors on both hands and 2 sensors on both knees or both feet. Some studies further limit the number of sensors up to 3 sometimes, where one sensor is on the hand and 2 sensors on both hands. Or we could go to the extreme case, which is using just one sensor on the head. Okay, then when solving the problem that I mentioned, there are several fundamental challenges to be addressed. When predicting a posture from IMU sensors, it is important to get correct orientation and positions of the sensors. IMU sensor inputs are angular velocity, as shown here, and we can also have a linear acceleration. So absolute orientation can be computed integrating the angular velocity one time, but whereas absolute positions here can be computed by integrating the linear acceleration 2 times, as shown here. Because chip IMU sensors have many sensor noise, which cause accumulation of errors, especially when performing double integration. So due to in other words, due to some error noise, it maybe if we do some double integration on the noise sensors, then the position can typically be incorrect. So if we maybe in the 3D space, if we plot the orientation or position of the IMU sensors, typically the orientations are quite correct if we use some sophisticated algorithms nowadays. But even with the sophisticated algorithm, if we plot the position in the 3D space of generated from the IMU sensor, they are typically drift easily along the time. So I mean, maybe after 10 seconds, maybe after 1 minute, you can see that there will be a huge difference between the ground truth position and the real ground truth position and the predicted position of the IMU sensors. So this is the problem to this is one of the challenges why the motion prediction from the IM sensors is quite challenging. And there is also another challenges, which is an ambiguity issue in a low sensor signals. So because IMU measures velocity and acceleration, as I mentioned, so if you think about what the velocity and the acceleration means, actually, it just means that IMU only captures the change of the motions. It cannot capture the absolute value or absolute position or absolute orientation. For example, the IMU cannot, as shown in this figure, the IMU cannot differentiate these two static postures, standing and sitting. Probably initially, when the actors change their posture, probably the IMU can see the difference. But if they just hold their posture for a while, then because the IMU can only capture the difference of the change of the motions, so the because of that reason, the two signals could just be can just converge to a single sensor signal. So probably if our model does not have any memory, or if our method does not have any mechanism to handle the history of the IM sensor inputs, then probably our model never differentiate between these two postures. So yeah, this is the another challenge. And finally, even if we predict perfect position and orientation from their IMU sensors, in theory, if we use a sparse IMU sensors, then there is some underlying challenges as shown here. So for example, let's say you have a ground truth, or we have a perfect position of the IM sensors. We have 6 perfect IM sensors here, but because of the sparsity, there might be many postures that correspond to these 6 sparse IM sensor inputs. So for example, let's think about let's think about the situation we have only one IM sensors on our head, then probably any low body motions or any arm position could be matched to the sensor signals. So which will make a lot of problem when using a sparse IM sensors. Okay, in summary, we have 3 main issues: the position drifting issues, and then history insensitivity issues, and underdetermination of posture issues. So typically in this research domain, most studies have been proposed new ideas to reduce these 3 issues. So today I will introduce 2 recent research results, and which are based on very different approaches. One is based on transformer here, and while the other is based on physics simulations. Okay. The first project that I want to introduce is titled Transformer Inertial Poser. The transformer means the transformer, inertial means the IMU, and poser means the system that's generating pose from the sensor inputs. That's why we name we use the name transformer inertial poser. So this is a joint work with the Stanford University, the Karen Liu and the Yifeng Zhang. And let me first demonstrate a real-time demo of our system. Here, the users on the video is currently wearing 6 IMU sensors, and you can see the reconstructed motions shown as a yellow character on the left screen here. The system, our system can handle not only normal behavior such as locomotion or sitting on the chair, but also extraordinary behavior such as crawling on the ground or swimming on the chair, like here. After minimal amount of calibration, which takes a few tens of seconds, the system can easily be adapted for other different users as well, who might have different body conditions. When compared to the previous users, the current user is 10 centimeters shorter, and the body proportion is also quite different. But you can see that our system can produce the user's full body motions accurately. Here is a comparison to the previous state-of-the-art system. The green character shows the ground truth motions that does not include the root joint trajectories. So the previous SOTA system transpose couldn't differentiate whether the signals were coming from the standing motions or the sitting motions due to the history insensitivity issues of the IMU sensors that I mentioned earlier. As a result, the pink character cannot sit on the chair correctly, where the sitting motions and standing motions keep alternating infinitely. On the other hand, we designed our system to have explicit memory to remember the previous state. So the yellow character on the right can sit on the chair correctly, and the artifact of alternating between the sitting and standing motions never happened, even in the long time experiment spanned more than a few hours. This is another comparison showing showing a benefit of our system. The previous SOTA system transpose assumes that users are moving on the flat ground. If you look at the left video closely, whenever drift in the vertical directions happens, the previous system simply changes the vertical location of the character so that the foot contacts are preserved on the ground plane. Due to this reason, we can see an artifact that it looks like the character is sinking to the ground. The more important thing is that this system cannot reproduce motions that occur outside of the flat ground. On the other hand, our system don't assume such strong priors on the contact point. Rather, we proposed and use stable body points, which are generalized contact points that could happen in any 3D space. Probably I will discuss about the details later. And those SBPs, stable body points, are represented as a red dot on the right video, where we can see that the yellow characters motions generated by our system successfully follow the ground truth stepping motions that occurs outside of the flat ground. Okay, and this is the actual motion prediction model used in our system. Let me talk about the details a bit. The inputs here are a sequence of IMU sensor signals, as I mentioned before. More specifically, we use a stream of orientations, R, and we also use our acceleration readings, A, here. Then from these inputs, the model outputs the current estimation of full body joint angles, which is represented as Q sub T. And then it also predict the root velocity here as well. And additionally, our model, as I mentioned before, also predicts some stationary body point, C sub T, to improve the accuracy of the reconstructed motions. The recent prediction, after it predicts some outputs here, the recent prediction are fed into the model for the next prediction, so that it can somehow, the models can understand what is the current prediction, and then we hope we designed the system to remember to consider the previous. We designed the system to consider the current prediction when they are predicting the next prediction. This is why we added some looping here. Then actually the mapping between the input and the output are trained by using transformer decoder. I guess that many of you are already familiar with what the transformer decoder means. And so this is the basics of our model and overview of our model. Then during runtime, we do some post-processing instead of directly using the predictions Q and V. Instead of just directly using this output, we do some post-processing. We have two post-processing here. The one is a smoothing filter, and then smoothing filter is just kind of average filter given the predicted posture, so that the generated output, generated motions does not have any jittery motions. And the second, we also do some contact filtering based on the predicted stable body point, which I guess is the main contribution of this project here. So let me go more into the details about what the contact filter means. Here, this figure on the right shows what actually SVP means. Let's say that this yellow box is a fit, and these three boxes are representing a moment where one of your fits is actually touching the ground while working. So in this, in the first figure, your heels are touching the ground, while your toes are touching the ground in the last figure. So here, again, here your toes are touching the ground, and here your heels are touching. Your heels are touching the ground here, and your toes are touching the ground here. So the key idea here is that when some of your body parts are actually touching something, and then there should be at least one point of there should be at least one point of which linear velocity becomes zero, right? So if you think about the physics, if something is touching the ground, I mean, there should be some point where the velocity is zero, right? And in a physical sense. But as shown in this figure, such zero velocity point doesn't have to be a static point on the body part. Rather, it can actually move within the body surface, right? So if you think about your feet are touching the ground, actually the zero velocity points can just move along your body surface, your feet surface. When you think about the physical properties of the collisions, or touching, or something like that. So our C sub t, which C sub t actually defined. So that's why we define the C sub t as a how to say so we to reflect this physical meanings, we designed C sub t to include the meaning of this physical quantities. So B sub t means that B sub t tells that whether there is any valid SVPs exist in the current body part, and the R sub t means that actually if the SVPs exist in this body part, then R sub t means where actually it is. So B sub t in this case will be 1 here, and the R sub t will be the vector from some reference positions. So fortunately, because the SVPs are physical quantities, we can detect SVPs automatically by minimizing these analytic equations. So the first term here represents that a linear velocity should be close to 0. And then second term ensures that it should not change too abruptly. So by minimizing these objective functions, actually from the motion capture database, we can automatically find where the SVPs are. So by using this SVP informations and the IMU signal inputs, I mean, we can train our network. But the problem in our case was that, I mean, actually there is not much there does not exist a large data set that includes both the motion plus some IMU sensors. So, I mean, because we don't have such a paired data set, so instead of we create our data set ourselves by spending a lot of monies, we decide that we use our existing motion capture data set, and then we simulate the IMU sensor signals by just putting some virtual IMUs on the existing motion data set. So by using this simulation of virtual IMUs, we were able to create a large number of IMU sensor signals with our paired motion data set. So more specifically, we used ANS data set, which includes 40 hours of motion. So in other words, after this process, we have 40 hours of paired data set between the IMU sensors and the motions. By using those data sets, we trained our model. Okay, then let's have a look at more results. By using the predicted SBPs, not only we can just increase the motion quality a bit, but also we can reconstruct surrounding terrains approximately. If some SBPs are turned on, we can use them as a constraint for fitting the ground surface. Conceptually, it would sound similar to SLAM, simultaneous localization and mapping, if you are already familiar with some robotics technique. So in the future, we might be able to construct 3D maps of your house or workplace by simply wearing smart watches and AR glasses that are equipped with IMU sensors by using our techniques. Okay, and that's it for the first project. And let's move on to the second project titled Human Motion Tracking from Sparse Sensors with Simulated Arbiters. The idea here is that we physically simulate users' avatar to generate physically plausible and natural-looking motions from sparse IMU sensors. So in a high level, the goal is the same as the previous project, but we use the very different approaches to achieve the same goal. So I hope that this comparing these two techniques will be very interesting for you as well. So in this project, we only use IMU sensors that are available from MetaQuest that includes one IMU sensors on the headset and two IMU sensors on the both hand controllers. The gray avatar on the right is physically simulated, and we train the controller actuating the simulated arbiter by using deep reinforcement learning. The goal of deep RL here is to follow the current input IMU sensor signals from the Quest as close as possible, which are currently represented as 3 axes or green dots located in the vicinity of the head and the 2 hands. Because we trained our controller for various users, so it can be used for different users, as shown in this video, who is much taller than the previous user. Not only just simple and typical behaviors such as working or learning, we can also produce free-form behaviors such as sketching while standing and some weird dancing as shown here. Okay, here is an overview of the system. Let me first explain how the system works during the runtime, assuming we already have a well-trained controller. So here we have a controller network in the middle. So observation from the user is a set of IMU sensor signals from the Quest, which will be coming from the real users. And observation from the simulation is the current state of the simulated avatar, which are positions and velocity of the all body parts of the simulated avatar. So from these two observations, the controller computes an action here, which is actually a set of forces applied to each joint. then physics simulator here compute the next state based on the forces from the controller and based on the previous state by solving equations of motion, which is simply speaking, which is just equals to which is F equals to ma in a high level state in a high dimensional state space. This process just repeats until the system ends. So how we can train the how can we train the controller then? Then, as I mentioned, we use deep reinforcement learning to train the controller. In the deep RL, the real function should be defined by ourselves to train the system. The real function is a function telling whether the current state or the current state transition is desirable or not. So at every time step, we compare the difference between the simulated avatar and the ground truth motions in a pose level with some prior terms. The difference here is then converted into the reward functions. Then it will be the main signal for the learning our controller. This is the actual formulation that we used. So, but I'm not going into all the details, but here you can have an idea on what the real functions means, what the real function means in our case. So basically, given the ground truth pose and the simulated pose, we penalize the joint angle difference, and we also penalize joint angular velocity difference. We also penalize the link position difference and link velocity difference. The joint means just joints. The link means body part having some masses, and joint doesn't have any masses on it. So we also penalize some abrupt foot contact changes as well here, so that the foot doesn't have any jittery motions during the training. So by using these real functions, after we computing the difference, we just multiply some weight, which is defined by manually. Then it will be our real function to train our control policy, or in other words, controller. For the training, we used 10 hours of in-house mocap data that include diverse behaviors. And we spent 2 days, we typically spent 2 days on our workstation to run deep RL algorithms, which is CPU in our case. So for the training, we used NVIDIA Isaac Sim, and during the training, we create 14 billion training tuples during the training, which is approximately equivalent to 13 years of human experience. But due to the power of the Isaac Sim, so we were able to create 14 billion training tuples within only just 2 days by using the single GPUs. After training, as I showed before, it can track users' motions pretty well for various behaviors, including standing, working, and running, like here. And surprisingly, for some specific behaviors, the system can even produce plausible motions from the headset input only. Here, the user only wears the headset, as shown on the upper, as shown in the video, as shown in the upper video. The users only wear the headset, but our system correctly predicts the low body motions just from the single IMU sensor input, which is quite surprising to us as well. Another benefit of using physics simulation is that the simulated arbiters can interact with any object in the scene in a physically believable manner. Here you can see the avatar interacting with a ball and a box on the ground. We can also change the virtual flat ground plane as a loft terrain which is shown on the right. In this example, the first feedbacks from the loft terrain affects the state of the simulated character, and our controllers are creating plausible response. Our controllers are able to create plausible response from the first feedback from the loft terrain. So to generate motions for user-driven virtual avatars, I demonstrate the two solutions based on IMUs. So although both solutions are using deep neural networks, the way of using it is very different. In the first project, we trained a complex model with some memory, and it directly outputs the user full body motions given sensor inputs. In short, growing the model complexity was very helpful in this case. On the other hand, the neural network model used in the project below is very lightweight. It is just 2 layers NLP, and it also doesn't have any memory in it, clearly. So instead, instead we combine this simple MLP model with the physics simulations, where the physics simulator plays as a good motion prior, while the previous histories are all maintained in the state of the physically simulated avatars. So in short, we reduce the burden for the model by using a strong prior based on the physics simulations. So both directions have unique pros and cons. So we want to study both directions further in the future. All right, and let's move on to the autonomous virtual avatars from now on. I think I have probably, I can use 10 minutes more. So I will just briefly explain, and I will just show some videos about it. So basically, autonomous avatars are avatars who are not tightly coupled with any direct control signal from users. So in Metaverse, anonymous pedestrian on the street or clock in the shopping mall can be examples of autonomous avatars. As shown in the right picture, virtual training opponents can also be autonomous avatars as long as they are not directed by other users. The key factor for autonomous avatars is that they need to be able to make a decision themselves, and they need to be able to behave or move by following their own decision. So the left figure describes this mechanism in a very from a very high level perspective, where the external states such as surrounding environment are given to our model. Then the model needs to produce full body motions of which context matches to the current external state. So if we also think about the input and the output, the model we want to make is quite similar to some behavioral systems. So in this talk, I want to introduce just my recent project for autonomous virtual avatars, where I developed a framework that can learn fighting strategies for virtual avatars performing 2-player competitive sports, which are boxing and fencing. Let me first explain the entire framework by using the boxing environment, then show you the fencing environment later. So this is the boxing environment, where the size of boxing arena is approximately 5 meter by 5 meter, which is quite similar to the size of a real boxing arena. So one round time is about 60 seconds, and the two players, the player who inflicts the most damage on the opponent wins the game, like a real boxing. So basically, these two boxers are physically simulated as well. So based on this physics simulation setup, we can use multi-agent reinforcement learning with competitive reward to train control strategies for the two boxers. This is one of our results, where each boxers move around with light steps when the opponent is far away in each other, and keeps the opponent in check by using light jabs when it is slightly farther than the reach. When the opponent is entirely within reach, the boxer punches the opponent repeatedly while blocking or avoiding the opponent's attack. If the boxer is held in a corner like here, then sometimes they try to reverse the situation by using the loops in the arena. This is the first-person view of the previous video. If we replace one boxer by a real user who is wearing a real headset, then real users will be able to practice or play boxing games, be able to play boxing as shown in this video. So basically, I mean, our autonomous avatar trained by algorithm can be our opponent for the real users. Okay, let me skip the details of the method, and let me just show you some visual demo how the training process goes on. Because we learn competitive policies, so the progress of learning does not increase monotonically as it often does in a single agent RL or cooperative multi-agent RL. In our experiment, we observed actually five different stages of learning. In the first learning stages, the player learns to stand in place without losing balance. Then they start to move around the arena in the second stage. While moving, there could be unintended collisions between the boxers. But regardless of whether it is intended or not, the boxers get the reward when the glove hits the opponent. And this kind of randomness helps their policies learn to punch. So as the learning continues, the punches become stronger and more accurate because the boxers are penalized when they punch each other. So they start to learn avoiding or blocking the attack in the first stage. After learning the basic skills for the game, such as moving around the arena and punching or avoiding, high-level tactics for maximizing damages on the opponent start to emerge. For example, the player uses light jabs to feint the opponent, or they sometimes utilize nearby loops to maintain balances easily. This is the end of the boxing, and let's move on to the fencing environment. Basically, the player who first touches the opponent wins the match, similarly to the real fencing game. However, the match can be called a draw if the player successfully counterattacks the opponent within 1 second from the first touch, like a real fencing game. These are the two fencers controlled by the fighting strategies that learned by our framework. And the red and blue lights on the ground indicate whether the fencer successfully touched the opponent or not. In our experiment, one fencer typically learns aggressive tactics, while the other learns to stay in place and play defensively. Similar to boxing, we can replace one fencer by a real user so that the users can practice or play fencing in Metaverse applications. All right, and let me conclude my talk. In this talk, I introduced a method of generating plausible motions for the two types of virtual avatars. One was user-driven avatars, and the other was autonomous avatars. And there are still many technical challenges in this research domain. First of all, we need to increase the prediction accuracy, especially for user-driven avatars. There are still a few centimeter gaps between the ground truth end effectors and the predicted end effectors, which might be noticeable for users in some situations. And minimizing such small gaps might be very important in some applications, such as virtual surgery training or some serious medical applications. Second, the current state-of-the-art model has 50 or 100 millisecond latency. So it should be further reduced in the future. Third, the state-of-the-art model has not been tested for a vast number of users yet. So I believe and I guess that unknown problems will occur when tested with many users in the future. Finally, in practice, there will be many heterogeneous users who are using different devices in the same metaverse applications. Some users might use sophisticated device while the other users might still use a legacy device such as a cell phone or laptop. In this case, the quality and the reliability of the motions we can get from each users will be different from each other due to the limited power of the legacy devices. Then we should consider in the future how we calibrate them to provide smooth interactions among heterogeneous users. And today, although I only mentioned how to generate motions for virtual avatars in Metaverse, the application of those techniques are not just limited to Metaverse. So motion generation or motion analysis in general is one of the classical research topics in many other research domains. For example, learning controls for physically simulated arbiters is directly related to designing controllers for leg robots. Due to this reason, I was also have been involved in other researches. This is the one example showing a model-based locomotion controller for quadruped robot, which is the A1 robot. I also used the deep reinforcement learning to train this controller. And as many users will use smartwatches or AR glasses every day in the future, I think we will be able to analyze users' full body motions for the entire lifetime. So as the accuracy of the human motion prediction becomes precise, I guess those collected those collected motions for the lifetime will be a good baseline for serious medical applications and sports applications as well. So our IMU-based motion prediction model might be very closely related to this area of research as well. So this is the end of my talk, and I'm happy to answer your question. And if you just scan the QR code on the screen, then it will direct you to my webpage, where you can find all the videos and papers there presented today. Yeah, thank you.